Hey guys, welcome to this Smoky Monday. What we're going to be doing in this video is we're going to be finishing your lecture notes for section 3.1. So if you can make sure to have those out. We're going to continue where we left off, and that was when we were looking at scientific notation. So to remind you with scientific notation, the first number in scientific notation needs to be a digit between 1 and 9. So this number can't ever be a 0, and it can't be like a double digit, like 10, 11, or 12, or triple digits in the hundreds. This has to be a single digit. So oftentimes you'll have a single digit, a decimal, and how many ever digits after that. So with this, our first digit is 6, and therefore our decimal needs to go there. It was previously here, and so we moved it to this position. So we had a little practice going from the standard, such as this long number in the mole, to scientific notation. So the decimal place was put in between the 6 and the 4 because that's our first digit between 1 and 9. And the decimal place was over here, and we had to move it over. So here's the rule. If your number is larger than 1, you're going to have an exponent that is going to be larger than 1. If you have a decimal that you're converting to scientific notation, that's of course less than 1, your scientific notation is going to have negative exponents. So this is going from standard to scientific with a large number that's greater than 1 and a small number that's less than 1. I'm going to go over a couple more examples. This is going to be going from scientific to standard. So let's have a number, and that's going to be 1.2 times 10 to the minus 2. This, of course, is in scientific notation. So take a look at the negative exponent. Negative exponent means that my number is going to be less than 1, meaning that's going to be a decimal. So I need to move it over 2 places. If I move it over to the right 2 places, 1, 2, it becomes 120. That number is not less than 1, so I need to move it to make a decimal by moving it over this direction. So I move it over 1 place, 2 places, there's my decimal, and I have to put my filler 0 in there, and so that will be my answer, 0.012. Now if I have a number such as 3.46 times 10 to the third, again, I have a positive exponent, which means I'm going to have a large number greater than 1. So I do not want to move the decimal place over this direction because that will create a decimal. So I want to move it over this direction, 3 decimal places. 1, 2, 3. There's my decimal, and so it would be 3,460. That's standard to scientific and scientific to standard. Percent error. So we've done 2 labs with percent error, but I want to remind you what the formula is. For percent error, it is going to be the difference of your 2 values divided by the actual. For example, let's say that we were trying to calculate the amount of salt obtained from a sample. Let's say that you measured, so you measured 1.27 grams of salt. But the actual value of this was 1.5 grams. So the actual was 1.50 grams. What's your percent error? Well, remember your percent error, here's the formula. It is going to be the actual minus the measured or the recorded all over the actual. So with this, in this case, the actual is larger than the measured, but let's say that my actual was actually less than the measured. You can always put your larger number here first because what this really is it's the difference. So it's the difference between these 2 values and you subtract them. So you always want to try to put your larger one first. just in case if you forget that, there actually is an absolute value symbol on the top here. In case if it does come out negative, it makes this value into a positive. We don't want to have a negative percent error, we just want a percent error. So that's the formula for this, and we'll go ahead and now we'll do this. What's the difference between these two? It's the actual minus the measured, or the measured minus the actual. It's the difference between those. I'm going to do my larger number, 1.50 minus 1.27, all over whatever the actual is. The actual measurement should be 1.50. We multiply this by 100 afterward. What this is going to do is this is going to give us into a percent. So if you took these values, 1.50 minus 1.27, put on your calculator, then divide all that by 1.50, multiply by 100, and you would get 15.3%. So this is another example showing us how to calculate error. So in this next section, I'd like you to try to see if you can do this by yourself to see if you know these. This is taking a look at the units for this chapter. It's the units for chemistry. We're looking at grams, Kelvin, liters, meters, and of course, moles. What I'd like you to do is try to fill these in right now, and I'd like you just to pause the video for a few seconds. I'm going to keep on going, but as you pause, no time is going to be taking place, and fill in these values. And then after that, we'll go over the answers. So please go ahead and pause the video now. Okay, hopefully you've finished that section and you've come back. So the amount is actually the content we were just going over, which is going to be moles. Amounts are measured in chemistry in moles. So that's going to be E. Length is not measured in miles, but it's measured in meters. That will be letter D. Mass, not measured in pounds, but it's measured in grams. So that's going to be letter A. Temperature is not measured in Celsius, nor is it measured in Fahrenheit. It's measured in what are called Kelvin. Kelvin is going to be letter B. And then finally, volume. Volume is measured in not gallons, but liters. So that would be letter C. That concludes the notes for section 3.1.